Hi, I'm Bob. Welcome back to 5 Minute Econometrics. In the past few days, we have examined how to use dummy variables as explanatory variables in the model to capture the difference in the outcome between two groups. We also use interaction terms involving dummy variables to describe different marginal effects across groups, or the difference in differences effects. The dummy variables in these situations are explanatory variables. They represent qualitative information, such as gender or policy, that helps to explain a continuous outcome variable. Today, we will explore the use of a dummy variable as the outcome variable. That is, the outcome variable is a qualitative event. We summarize the qualitative event with a dummy variable with only two values, 0 and 1. Dummy or binary outcomes include whether a person has a bachelor's degree, whether a firm receives a government subsidy, whether a city provides free bus services, or whether a country has a positive growth rate. In each of these examples, we can let the outcome variable y equal 1 to denote one of the outcomes, and y equals 0 to denote the other outcome. The model using a dummy variable as its outcome is called a binary response model. In a linear regression model, when y is a dummy variable, the coefficient beta cannot be interpreted as the change in y for one unit increase in x, because y either changes from 0 to 1 or from 1 to 0. Given that the zero conditional mean assumption holds, we can write the equation of the expected value of y. For a dummy variable y, the expected value of y can be interpreted as the probability that y equals 1. People also interpret it as the probability of success, since y equals 1 means the event occurs. So we have the linear probability model. It says the probability of success is a linear function of x. The coefficient beta j measures the change in the probability of success when xj changes by 1 unit, holding other factors fixed. To model the probability as a linear function of x is not the only way to describe the relationship between x and y. We will learn other binary response models later, such as the logit and the probit models. After regression, we obtain the estimated equation for the linear probability model. In the estimated equation, y hat is the predicted probability of success, or the fitted probability of success. The slope estimator, beta hat, is the predicted change in the probability of success when x increases by 1 unit, holding other variables in the model constant. Here's an example. The model relates the married women's labor force participation to their husbands' earnings, years of education, labor market experience, age, and the number of children under 6 years old. The outcome variable, labor force participation, is a dummy variable. It equals 1 if the married woman reports working for wages outside the home at some point during the year, and 0 otherwise. We use the tabulate command in Stata to obtain information about the dummy variable. Around 57% of the 753 married women in the sample were in the labor force. Using the OLS method, we obtain the estimated equation. I write it in the normal form. The standard errors are in the parentheses. To interpret the estimates, keep in mind that the estimates are the estimated changes in the probability of labor force participation when the explanatory variable increases by 1 unit. 1 more year of education increases the probability of married women's labor force participation by 0.039 or 3.9%, holding other factors constant. An additional $1,000 in non-wife income reduces the probability by 0.3%. 1 more year of work experience raises the probability by 2.2%. 1 year older leads to a 2% decrease in the likelihood. Finally, 1 more kid less than 6 years of age reduces the probability of married women's labor force participation by 27.5%, which is a huge impact. The estimates are statistically significant at the 1% level against a two-sided alternative, except for the husband's income, which is significant at a level above 2.5%. When dummy variables appear as both the outcome and explanatory variables, the coefficient measures the predicted difference in the probability relative to the base group. For example, we define a dummy explanatory variable, kid. It equals 1 if the married woman has a child under 6 years old, and it equals 0 otherwise. In our example of 753 married women, 147 have at least 1 child less than 6 years of age. We included in the model instead of the continuous variable kid less 6. The estimate of the coefficient of the dummy variable is minus 0.34. It means compared to the married women without children under 6 years old, those having a child under 6 are 34% less likely to take part in the labor force, holding other factors fixed. The estimates for the other explanatory variables in the model do not change substantially. The percent correctly predicted is a measure of the model's goodness or fit. It is the proportion of correct predictions among all predictions. Notice that the predicted value of the outcome variable y hat is not a dummy variable, but a continuous predicted probability with most values between 0 and 1. We cannot directly compare the predicted probability with the actual values of the outcome variable. We need to define a dummy variable y tilde, which equals 1 if y hat is greater than 0.5 It equals 0 if y hat is less than 0.5. Then we compare y tilde with the actual values of y. The proportion of correct predictions is the percent correctly predicted. In our model, 460 of the 753 married women are predicted to participate in the labor force. We use the tabulate command followed by the two variables to see the two-way table of frequencies. The first row shows that 210 of 325 married women who did not work are correctly predicted. The second row shows that among 428 married women who worked, 345 are correctly predicted. Overall, 210 plus 345 equals 555 observations that are correctly predicted. It is 73.7% correctly predicted. It is a decent prediction. The advantage of linear probability model is that the coefficients are easy to interpret. They are the estimated change in the probability of the outcome given a 1 unit increase in the explanatory variable, holding other variables in the model fixed. And the estimates are accurate around the average values of the explanatory variables. However, it has some limitations. First, the fit value of y could exceed the range between 0 and 1. Remember that the expected value of the outcome variable is the probability, which must lie between 0 and 1. However, in the estimate model, some y hats could be negative, and others could be greater than 1. Let us have a look at the predicted values of the probability of labor force participation in our model. We use Stata's predict command with the XB option to store the predicted values of y. We use the summarize command to find the information about the predicted values. The minimum value is below 0 and the maximum value is above 1. The count command shows that 10 predicted probabilities are less than 0, and 21 predicted probabilities are greater than 1. These predicted values are not good fits for the probability. In addition, the linear probability model implies a constant marginal effect of x on y. For example, one more kid reduces the probability of married women's labor force participation by 27.5%. It implies that the effect of going from 0 kids to 1 kid is identical to the effect from going from 1 kid to 2 kids. However, it is more realistic that the first child will affect her mother's willingness to work more than subsequent children. Today, we discussed the dummy outcome variable and the linear probability model. The dummy outcome variable represents whether a qualitative event occurs. When we use a dummy variable as the outcome variable in a linear regression model, it is called a linear probability model. The coefficients in the linear probability model measure the change in the probability of the outcome event occurring when the explanatory variable increases by 1 unit, holding other factors constant. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.